our findings for how locally adapted populations respond to climate change and how this can affect potential divergence between populations as well as have impacts on other populations in the community. So when we're thinking and trying to understand how populations are going to respond to climate change, we want to know if and how they might adapt to these changes. And beyond the population level, we have to think about how there could be extending consequences for impacts on the community, and think about potential changes to ecological and evolutionary processes that maintain or generate diversity. So a major consequence of climate change includes shifts to life cycle timing or phenology. So periods of growth, development, dormancy, and reproduction can shift under climate change scenarios. And there are numerous examples of these kinds of shifts across different taxonomic groups. In a community interaction, shifts in life cycle timing can have a number of consequences, including things like asynchrony across trophic levels, like between predator and prey, and for divergence between populations when time is a major component of isolation. So here we're asking about how climate change can affect life cycle timing and community interactions in the Rhagoletis pomonella species complex, where adaptation to different host fruits has facilitated divergence and speciation in a suite of populations. Today I'm focusing on the hawthorn and apple host races. And this shift happened about 160 generations ago with hawthorn flies moving over to apple. And the differences between these flies is driven by adaptation to these different host fruits, in large part because the fly life cycle is under strong selection to be matched with the timing of its fruit. So the fruit's important for mating and oviposition. Females deposit their eggs inside the fruit. That's where larvae develop. Then they emerge and go through their pupal stage in the soil, and then eclose later as adults. And because of these differences in phenology, there's temporal isolation between the host races. And in addition to habitat isolation from divergent olfactory preferences, that results in an overall gross migration rate of about 4% per generation. So still some gene flow going on, but limited. Another level of complexity in this system is that the flies have 3 species of wasp parasitoids. And there's this really interesting dynamic of cascade divergence, whereas the flies moved over to this new host, their parasitoids shifted with them in their life cycle timing. So today I'm going to ask about effects of climate change on life cycles of the flies and wasps, interactions among trophic levels and whether synchrony is maintained between flies and their parasitoids, and then impacts on ongoing ecological speciation. So this is our study design. We have insects on both host fruits under warm and controlled scenarios. And for the flies, previous work has shown that temperature is a critical cue for development. So I developed these programs for different temperature regimes that have natural, daily, and seasonal fluctuations. And this is based on a 10-year average of soil data from 2007 to 2016. And then the warming condition follows that same daily and seasonal pattern, but all the temperatures are increased 3 degrees Celsius. And this extent of shift is based on projections for 2050 to 2100 for the Midwest under multiple emission scenarios and from multiple sources. Okay, so here we're testing the effects of warming on fly survival and life cycle timing, as well as that for the wasps. We also measured lifespan and fecundity to look at potential trade-offs between development time and energy spent in development and these measures of adult fitness. And we measured sexual isolation with mass mating trials. So this included over 6,300 flies individually tracked from larvae to adulthood. I'm focusing today on these first 2 components. But earlier in the meeting, an undergrad leading the sexual isolation component of the work presented a poster. And if you track her down, I'm sure she'd be willing to tell you about it. So we collected fruit infested with wasps and flies from natural populations in a St. Patrick's site in Illinois. And this is in August and September, depending on when these fruits are in season. And this is what a minivan full of 700 pounds of apples looks like. So yeah, there was a lot of picking of things out before you could return to that van. So with an amazing team of undergrads, they helped me collect larvae from these fruits as they emerged, sorted them out in their pupal stages, put them individually into tubes, track them every single day to quantify life cycle timing and survival. So flies can develop directly into adulthood, but they often go through a period of suppressed development called diapause. And so this is an adaptation to avoid unfavorable conditions. You're looking at a timeline across the year with winter and apple fruit availability as an example. So flies that develop directly have no fitness. There's no host fruit available for them to reproduce. But if they go through diapause and delay their development before and after winter, then they develop and reach reproductive maturity right before this fruit is available for them. So diapause is critical for adaptive life cycle timing. Our first question was how warming affects life cycle timing in the flies. And I'll show you what happened with some of these flies that had closed pre-winter. So remember, this is flies that aren't going to survive to breed. So ideally, highest fitness is if we have 0 for both of our fruit treatments and under control and warming scenarios. And that's true for hawthorn flies, but not for apple flies, where in apple warming, almost a quarter of the population encloses pre-winter. So we see an asymmetric effect of warming on the host races, and especially for apple warming flies, they're going to suffer greater mortality before breeding. We also looked at what happened to any of the flies that didn't enclose during the breeding period. And so for the start of their second winter, we quantified how many adults had died at different life stages and whether they were still alive and thus might have gone through a second diapause. So this allows us to pick apart the proportion of dead individuals across all our treatments, those that have closed post-winter, those that have closed pre-winter, we just looked at this pattern, and those that could have gone through a second year of diapause. And one unexpected thing that we found in the hawthorn flies is that warming kicks more of these flies to close post-winter rather than go through a second diapause. And so what's really interesting is that warming pushes both of the host races to close earlier, but it has different consequences, right? So warming, apple flies are coming out pre-winter, which is non-adaptive, and for the hawthorn warming, more of them are coming out during their first breeding season, maybe than during their second. So that has effects on these breeding population sizes. So under apple warming, we have fewer individuals that would survive to breed, and for hawthorn warming, more of them. So now I want to show you what the timing pattern looks like of eclosion post-winter. So these are going to be in the reproductive population. So I have date along the X and number of enclosed flies on the Y. And you can see that apple warming in yellow is shifted earlier in the season than apple control in blue, significantly shifted. And the same pattern is true in hawthorn. So in that orange color, hawthorn warming is shifted earlier. We looked at this another way, looking at cumulative eclosion curves. So I have days to eclosion on the x-axis of both of these graphs from the spring equinox, which is when temperatures shift from winter to spring conditions. And then the cumulative proportion of eclosion from 0 to 1, and so that's changing over time. So again, here we can see the shift between warming and controlled conditions. And this comes from a type of regression analysis called accelerated failure time analysis. And it allows us to test for the differences in the timing of probability of events. So the z-score here is analogous to an F from, say, a NOVA. And so this gives us strong statistical evidence to be able to say that these host shifts, or these shifts in response to warming are happening. And interestingly, when we look at the host races together, there's an asymmetry in the extent of that shift. So apple flies are shifting more in response to warming than hawthorn flies are. Okay, so the flies shift, but what happens to the wasps? So here's the flies, the wasps don't shift. So warming doesn't shift the wasp eclosion curves. These 95% confidence intervals for warming and for control under both host races completely overlaps for those eclosion curves. So this would generate asynchrony between the wasps and the flies under a warming scenario. And lastly, we asked about potential impacts on divergence between these two host races. So now I'm showing you apple and control together under the same temperature treatment. So here's control and then here's warming. And so we measured temporal isolation. In general, if the distributions overlap completely, there's no temporal isolation. If they're completely separate, that's Ri of 1. We use the general equation of looking at the number of heterospecific interactions possible over the total that were possible. And we extended some existing equations to allow us to look at the potential differences for each sex of of each host race. So we can look at how differences in timing of male and female eclosion could impact temporal isolation. And what we find is that temporal isolation is stronger under controlled conditions, about 0.44, and weaker under warming. And this is about a 25% reduction in temporal isolation, which could have a really large impact on the potential for gene flow between these host races. So to sum up these components, for life cycle shifts, we found asymmetric effects on adaptive responses. So these apple warming flies shift to coming out pre-winter. That's going to decrease their breeding population. And so this suggests apple flies are closer to their temperature threshold, and their adaptive capacity for responding to climate change is likely more limited than in hawthorn flies. We also found that there's an asynchrony between wasps and flies, given that wasps aren't paying attention to temperature. They're likely using cues from other sources like photoperiod or even the circulating hormones in the flies themselves to set their biological clocks. And then lastly, we find evidence that temporal isolation would be decreased and allowing a potential disruption of the current migration selection balance with the possibility of collapse isolation over time. So our current goals involve using genomic analyses to understand how underlying genetic and genomic variation set the stage for potential responses, as well as how climate change can shape genomic variation. So we're going to look at the effects of standing genetic variation on facilitating rapid evolutionary responses. We'll look at the potential constraints of genomic architecture and being able to respond, and look at the effects of climate change on genomic divergence between these two host races. And so more big picture, as we think about how populations respond to climate change, this is in the context of really complex ecological and evolutionary processes, like multiple selective sources and interacting features going on, and then these community interactions that we have to take into account. And so the consequences of climate change might be really complex and difficult to predict. So in our cases, we have multiple asymmetric effects of warming, which have drastic fitness differences for these two host races, even though they're at the same site and they have lots of similarities in their genomes. And so as we move forward and want to make strong predictions for how populations will respond to climate change, the more we can design experiments with biological realism and nuance and complexity that matches natural systems as best we can, that's going to strengthen our ability to really understand how populations are responding to climate change and what kinds of consequences can reverberate throughout the community. So with that, I want to thank my collaborators, especially Tom Powell at Binghamton University, our funding sources, and thanks for sticking it out to the end of the day. Yeah?
So I just noticed that in both cases with your control and your warmer treatment, the apples seem to have a bimodal distribution of divergence. Do you think that there's a possibility that there could be increased selection on the early eclosion to reinforce the temporal breakdown if it were to happen?
Yeah, so the shape of the selection curve we haven't looked at, but certainly given that there's variation in eclosion timing, there's the possibility for selection to shape which individuals with which type of eclosion patterns are those that are surviving. And so there is the potential for across generations to find higher proportions of adaptive responses given the apple flies that survive.
Is there any, sorry, follow-up.
Yeah.
Is there any ecological reason for that bimodal curve that you have, have you speculated at all on why there's a bimodal distribution?
I don't know that I specifically made predictions about that, but that there's lots of variation among all the host races in their eclosion timing. And so, yeah, so some of that could come from the hawthorn variation that was available and sort of like how that's been shaped as they were drafted to apple. Yeah, thank you. Yeah.
Do you have any background knowledge about how the host plant's phenology responds to the climate change?
Yeah, so we looked at these two trophic levels, but surely the plants have capacity to respond as well. And so because of agricultural records, we have a much better sense of what's happening with apples because people are paying attention to that. And it does seem that they are also shifting earlier. So some of these shifts that the flies are doing might match their host plants, but we don't have as much information for hawthorn. But that's an important component of this community interaction.
Yeah, I was thinking maybe you can use the geography to replace the climate change thing. You see the phenology differences between different latitudinal gradients and
Yeah.
see whether that could be a replacement of like to see how host plants respond to the climate change.
Yeah, so using the parallels of the geographic variation to make predictions about change over time. Yeah, definitely need to take a look at that. Thanks. Okay, I'll stick around in case anyone else wants to ask anything or